Yeah, today's a really important day because we learn about the adiabatic relationships. We've already talked about reversible isothermal expansion and compression. And so today we're going to learn about adiabatic expansion, adiabatic compression. And so they're both reversible processes. So they're continuous lines that we integrate. We'll see in a second. We'll integrate with respect to volume, and like we did with the isothermal relationship, we integrated from an initial pressure to a final pressure, and an initial volume to a final volume, and we got that curve, and we got every little bit of work that was done under that curve. We'll do the same thing with the adiabatic expression. And so for isothermal expansion, as we're expanding from this initial volume to this final volume, in order to stay isothermal, see that if we just expand, the gas cools because we're getting rid of the intermolecular attractions. So if the molecules have to be further apart because they're taking up more volume, then it's going to cool because you had to break the hydrogen bonding or the polar attractions. So in order for it to not cool, you have to put in heat. So if you want to stay on an isotherm, you actually have to put heat in while you expand. So that, because you're adding heat, the pressure is higher than it would be if it just cooled. So in an adiabatic expansion, if you don't put in heat, not only do you expand, but the pressure drops more because you're cooling. So during an adiabatic expansion, you're cooling. You're not on an isothermal because it's isothermal. It's the same temperature. So there's no heat flow in an adiabatic expansion. You're not putting heat in to maintain a temperature. And same thing with compression. There's no heat flow in an adiabatic compression. So it heats up when you compress it. And then if you were to compress it isothermally, you'd have to sink the heat. So as you're pushing these molecules together, they're forming their associations. It's exothermic, and so they're giving off heat. And if you don't let that heat escape, that heat generates more pressure, and so it's steeper and it goes up to a higher pressure. And it raises the temperature of the system. And so we'll derive this relationship today, this pressure volume relationship with this gamma. But we'll talk about this gamma, and we'll compare it to the isothermal. So this is kind of, we're deriving all of this stuff today. But the bottom line is, you see this adiabatic, it's a steeper curve in a PV diagram. So a pressure volume diagram, the adiabats are steeper than the isotherms. So we can have lots of isotherms, right? You think about just any temperature. You have that isotherm, you have this isotherm. Whoa, I'm trying to do my best there. And this isotherm here. Maybe this isotherm here. So those are the isotherms. They're not exactly parallel, but they're kind of parallel. In the small region, they look very parallel. Okay. And so if you'll notice, this adiabat comes down here. If we were to draw another steep adiabat here, it would connect this temperature, T hot, to this temperature here, T cold. And if we were going in this direction, like this, and then we did a compression here and a compression there, we have a cycle. You see that cycle? So we can take two isotherms and two adiabats and couple them together and make a cycle. And that's actually the perfect cycle. That's the best we can do. It's following all four legs, making them reversible. Then that's the most precise way we can generate a cycle, and it's going to give us the maximum amount of work. It'll be the most efficient cycle that we can make. So it's very important to understand isothermal equations and adiabatic equations. So today we're going to talk about the equations and how to come up with the state variables, and then next time we're going to actually calculate the work and the heat and all of the thermodynamics behind those things. So this is this idea where we have a temperature change. So if we have a temperature change, we have a change in internal energy. And since Q is 0, then the change in energy is just the work. And so the work done is the number of moles times the heat capacity at constant volume times the change in temperature. Now for an ideal gas, we have these relationships, these adiabatic relationships. But this is the important piece down here, this gamma. Gamma is the ratio of Cp to Cv. And so we know that Cp is equal to Cv plus R. So it's always greater than Cv. And so gamma is always greater than 1. The question is just how much greater than 1 is it? Because different kinds of gases are going to have different CVs. We have monatomic gas, 3 halves R. We have a diatomic or a linear gas, 5 halves R, or like water, a bent molecule, asymmetric molecule. Then it's going to be what would we say? That'd be 6 halves, yeah. And so then we can calculate CV, and once we know CV, then we can calculate CP. Now let's try to find the equation for this curve. One thing we can do though, and because we're dealing with state variables, if I want to know the initial and the final, I don't have to necessarily follow this line. I can say, all right, at this temperature and volume, I can calculate this change from that temperature point to that temperature point, and I know the change in internal energy. And so I can calculate the amount of work just from that particular equation. What I can't do very easily is calculate this final volume. So when we're figuring out the state variables table, we typically have 2 out of the 3 variables. We have an initial volume and maybe both temperatures. Or we may have the 2 volumes and only 1 temperature. So we're always trying to find that 4th variable. And so let's look at some of those relationships. So this is what it looks like in 3 dimensions, actually. So when we were looking at a PV diagram, we were staring at this diagram, from this sort of PV plane. So we're staring at it at this direction. And so we saw the isotherm here, and then we saw the adiabat. See how the adiabat is steeper? It rolls more downhill, more directly downhill. Whereas the isotherm, in order to maintain the same temperature, we have to put heat into the system. And so it follows the temperature line. So this PVT diagram, that's the 3-dimensional phase diagram where pressure is plotted versus volume and temperature. Likewise, down here, there's going to be an isotherm. So there would be a spot like this. Gosh, it's so hard to draw. Okay. So that would be an isotherm. So this would be T hot. This would be T cold. And there may be like an adiabat up here that connects them up here at a higher pressure. And so once again, this would be the cycle. So there'd be a little bit of an isothermal here. There'd be an adiabatic expansion here. There'd be an isothermal compression there, and an adiabatic compression there. And so again, you can have that cycle, and this is the pressure, temperature, volume relationship in this 3D phase diagram. Now I call it a phase diagram, even though we don't have any other phases on here. This is just a smaller portion of a bigger phase diagram. This is just the gaseous region. So we're dealing with gases as working fluids. If we were to cool the temperature down, shrink the volume, then we would find the liquid region, and then we would find the solid region too, at even smaller volumes. So we compress it and cool it, we get it to condense. It becomes a liquid. We continue to cool it, we would become a solid. And so we would have those solid and liquid regions down in this direction. But for these working fluids, if we're going to push pistons, we need a gas. So all these engines work with gases. So let's derive these relationships. So if we take this first law, so the change in internal energy has 2 ways to change. You remember cash and credit, right? It can be heat or work. So we have heat or work, and we're dealing with an adiabatic expression, or adiabatic relationship, an adiabatic expansion. And so this Q is equal to 0 here. W, now we have an isothermal we've integrated the isotherm and come up with a work for isothermal relationships. But we're going to do this time, we're going to integrate with respect to volume. And so with this P external dV, and then we have, this is the internal energy change. So this is just all right here. So work is this piece, internal energy is that piece. We have dV on the right and dt on the left. We'll just integrate both sides. We'll integrate the left side with respect to temperature and the right side with respect to volume. And so P, right, how do we get rid of pressure? Well, P is equal to nRT over V. And so we took that T on this side and we moved it over there. So this is the T from the pressure. So it shows up over there. And then we have nR over V on the right. So we just separated our variables, got temperature on the left, volume on the right. And now we can integrate both sides from volume final to volume initial. And we're ready to go. Okay, so what is this integral? I mean, we have dx over x, it's going to be natural log. So we have the natural log evaluated at ti minus the natural log evaluated at tf. And so since the difference of logs is the same as a quotient inside the log, we have this natural log of ti over tf, natural log of vi over vf. We have ncv and nr. We can cancel the n's, leave everything in molar relationships. And then r, you could essentially think of r as Cp minus Cv, right? Because Cp is Cv plus r. So we could substitute that, and then we have Cvs and Crs in our equation. So that's what we've done here. We got rid of the n's. We looked at that relationship between Cv and Cv and Cp. We've brought Cv over to the other side, and we split that denominator so that I have this piece here, which will become 1. So we have Cp over Cv, which is equal to gamma. So I have gamma minus 1. And then we have these relationships. Well, that can be an exponent. If it's out front, this can come over here to the top. And then I can get rid of the logs on both sides. So that's our relationship between temperature and volume. So if I know the initial volume and I know the change in temperature, I can calculate the final volume because I know my Cv, which then allows me to calculate Cp. And if I know these three, then I can calculate the fourth. So this is important because we've got to know how to calculate our state variables before we can calculate any of the change in volumes and work and all of that stuff. So the first part in any kind of cycle problem is coming up with the state variables at point A, B, C, and D. Anything that caused you trouble on this?
What is the negative though?
Negative. This guy right here? Where does it go? Oh, I flipped these two. So VI and VF flipped.
Okay.
That's where it went. Yeah. And that gets the correct relationship here. Yeah. So that's where the negative went. So cancel that out and point to the arrow. Okay, good eye. Now this gives us a handy equation if we have both temperatures in one volume or both volumes in one temperature. But what if I don't have any temperatures? What if I have pressures? So can we rewrite this equation in terms of the other state variables, right? Because we have relationships between pairs of variables. We have relationships between temperature and pressure, or temperature and volume, or volume and pressure. So we can come up with all three of those, and they're really handy. So if we take that equation, now we could invert that. If we raise both sides to the 1 over gamma minus 1, then the gamma minus 1s cancel. But then over here, then we have this to the 1 over gamma minus 1. So that's how we get this relationship. It's just kind of for convenience, like for your calculator, right? If I know my temperatures and not my volumes, then I can put my volume initial here, and I put my temperatures in, and then I can do that. So you'll get really handy, really good at using the gammas and gamma minus ones and 1 over gamma minus 1 and so on. So once you find gamma, it's pretty easy to do these relationships. Now, if we take this top one, we could take the temperature and substitute, PV over NR, and we have initial volumes, initial pressures, initial numbers of moles, and so on, and then cancel the things that don't change, and so we end up with this particular situation. So if we put in that, and the number of moles hasn't changed, and the number of and of course the gas constant doesn't change, then we have P initial, P final, V initial, V final. And so we just need to simplify this one, and we'll have the relationship between pressures and volumes. So we need to bring this over to the other side. And so we're going to get that gamma minus 1 plus 1. We'll have another one of those on there. And so we'll end up with the P initial over P final equals V final over V initial raised to the gamma power. And so that's a really handy relationship. If I've got 2 volumes and 1 pressure, then I can find the second pressure. If I have 2 pressures and 1 volume, I can find the second volume. And again, we know gamma because we went through that whole lecture and even an exam on how to calculate CV. If it's a monatomic gas, or if it's a linear molecule, or if it's an asymmetric bent molecule, if the vibrations are activated or not, So we went through and calculated all of those CVs, and then for CP, you just add another unit of R, and then you take the ratio and you get gamma. So we have to have those gammas to get these adiabatic relationships. Now, an isotherm has a gamma of 1. If you were just to take the ideal gas law and see how it depends upon volume, the N and the R and the T have canceled. And so, the pressure is inversely related to volume. So PI is on top, VI is on bottom. So this would be the ideal gas law at an isotherm. The temperatures cancel because it's the same temperature. Okay, so this is a gamma of 1, right? This is raised to the gamma, and if gamma equals 1, it's an isotherm. What about for helium? So for helium, we have this ratio of Cp over Cv. We can look at that and see that it's 5 halves R over 3 halves R. So where do 5 halves come from? Well, we know that Cv is 3 halves, and we add another 2 halves because we're adding R, another unit of R for Cp. So it's 5 halves R over 3 halves R, so we can cancel the halves. And so that's going to be our gamma for helium, 5/3. So we get some really weird fractions, 5/3. You wouldn't look at that and know immediately, that that's what's going to happen for helium, but it's because you're taking that ratio of 5 halves over 3 halves. So that's 1.67. So if we look at this relationship, that's for an isotherm, it's this steep, right? It's this ratio of volumes raised to the first power. What about the ratio of volumes raised to the 1.67th power? That's going to be steeper, quite a bit steeper, like 1.67. So the helium would have a much steeper adiabatic. And when you were to do an expansion or compression, if you do an expansion, it's going to cool even more than isotherm or these other gases. Okay, let's look at CO2, which would be the same for any linear molecule. So for this, we have Cv equals 3 halves for translation, 2 halves for rotation. And why is it only 2 halves? Because it's linear. It doesn't have rotation around the symmetry axis. It only has the tumbling rotations. So rotation around X or Y. And then vibrations, I would say 0 active vibrations. And all of that's times R. So that's where the 5 halves comes from. And then we add 2 more halves for CP. Let's add another unit of R, so we end up with 7/5 or 1.4. Since gamma is smaller, then the adiabat for CO2 or any linear molecule is going to be not as steep. So it's going to come in like this. So CO2 would be a gamma of 1.4. It would not be as steep. So for water, let's see if I can write this down here. If I try to write down here, I'm going to get into my little tools area, so I'm going to have to write it up here. So for water, we have 3 halves for translation and 3 halves for rotation, plus 0 for vibration. See TRV, you got that? Okay. And so that's where the 6 halves comes from. Add another 2 for CP, so it's 8 halves. So we end up with 4/3 or 1.33. And so water is even less steep than CO2. So even though we use steam for all of our heat engines, almost all of our heat engines, it's not as good as if we used a monatomic gas. Like helium would be even better. We see this in effect when we do refrigeration. I haven't talked about refrigeration, but what is this heat engine? The heat engine is taking heat flow and generating work. So we put in heat, we cause it to go through the cycle, and as it goes through this spontaneous cycle, like our little Stirling engine that we had, it produces work and it spins a turbine or whatever. What if we ran that backwards? If we ran that backwards, we have a refrigerator. So putting work in can pump heat from one side to the other. And so the cryogenic refrigerators that we have, they get down to the lowest temperatures. We want those to be as efficient as possible, and they run on helium. So they'll have a closed loop cycle and really refrigerate things well. We have those running on helium. So this is our Carnot cycle state variables table. So this is the classic. I mean, seriously, this is like a big deal here. Like you could post on social media, learned about the Carnot cycle today, and you would actually get some engagement on that. Everybody that's been through PChem would be like, oh yeah, I remember that. Even like old timers, 70-year-olds, they would say, oh yeah, I remember the Carnot cycle. Because it's the best one. It's everything's a reversible. It's either isotherms and adiabats. And here's our state variables table. We have classically four points in the diagram. We have A, B, C, and D. And we need to know those points. If we don't know those points, then we can't calculate our heat and our work, and efficiency, and all those things. So at point A, we have P, V, and T. And N, I mean, we can put in a number of moles as well if we wanted to. We typically know VA and VC because a lot of our engines have two numbers that they give us. They give us compression ratio and displacement. And so, do y'all know the displacement of your automobiles? Do you know how big your engine is? A lot of times it's a number that's given for the machine, or sometimes it's put on the outside. Like mine is put on the outside to kind of brag about it. Like the manufacturer's like, I want everybody to know how big this engine is. I don't really care, but it's on the outside of my vehicle, I guess, for bragging points. It's a 5.7 liter. So what does a 5.7 liter mean? When I'm talking about my truck, the V8 gas-powered truck, 5.7 liters is this displacement. So my truck is 5.7 liters. And so that's the difference between VA and VC. So it sweeps out this volume. So this volume here to this volume here, that difference is 5.7 liters. That doesn't tell me what A and C are. It just tells me the difference between them. But I at least know that. And now, how do I get the values of VA and VC? I've also given the compression ratio. And so that's not on the outside of the car. I'd have to look that up. I might even have to measure it. So you can sometimes, in the old days, I don't know if you can still do it. You get in there and you pull off one of the spark plugs, okay, and you put a pressure gauge in there. You like screw it in or hold it in. Some of them you just hold it in, and you're starting at 1 atmosphere, right? And you turn the key, and it turns the motor over, and the piston pushes, and you go from 1 atmosphere to whatever the piston pushes, and so you get the max pressure. So the compression ratio would be, if you're measuring pressure. Okay, where's my pen? It would be over here. It would be this pressure to this pressure. And that's going to be related to this volume and this volume. So you measure that ratio of pressure 1 over pressure 2, that's going to be proportional to this VC over VA. And so look, we've got 2 equations and we've got 2 unknowns. So we can combine these equations and come up with what VA and VC are if we know the displacement and the compression ratio. And this little site here is an engineering site made for gaskets, but they have a nice little calculator on it. Look at all of the variables that you have in your engine. And you can put in, if you know the design of the piston, like the little headspace volume, that's the combustion chamber volume. In this particular case, I've got this 41 cc's, or this head gasket bore, the cylinder bore, the head gasket thickness, all of these different factors come in, and they can calculate this compression ratio here. And you know the displacement volume, the cylinder volume, and so then you can calculate your delta V, your VC minus VA, and so we have these two equations up here. Let's calculate now our VC and our VA. So if we take so we multiply up here both sides by VA, and so VC is equal to RC times VA. So if we knew VA, then we would be able to get that. We can take that VC piece here and plug it in to the delta V equation. So now I've got this equation. I know this number, I know that number, and I've got one variable, so I can solve for VA. And so then if I know, let's just solve for VA. So that's VA is delta V over RC minus 1. And then I can put that piece in to the other equation and solve for VC. So now look, I've got VA in terms of numbers I know, and they're actually tied to the actual construction of the engine. So the volumes you know by the engine because you designed the engine. And so that's probably the best one. We can always know the volumes, and that's why they're written on the outside of the vehicle or in the owner's manual. We know how the engine's constructed. The pressures change with the temperatures, and the temperatures change with how much gas you put in. And so this cycle will cycle up and down in terms of pressure by whether you step on the gas or not. You step on the gas, the pressures go up. It's a little bit more efficient. It's a little bit hotter. It pushes harder. You're going too fast, you let off the gas, the system slides back down, but the volumes never change. So we actually construct the engine with the volumes, and then we add more gas, change the temperatures, change the pressures, and so on. Now they're made to operate in ranges, okay? But once you're in those ranges, that's how you control your speed. Add a little bit more number of moles, raise the temperature. You have more efficiency, you can push harder. And then you want to cool it back down, you let off the gas, you're not pushing as hard, you're not generating as much work. And so here's stock engine data. Like you can actually go out into the internet. Here's for Nissan and Toyota. I went through and picked this row here for the Toyota. This is a 2.5 liter engine, a little bit more economic, I would guess, than my 5.7. Okay. So when we talk about the liters, I mean, this is cc's or cubic centimeters displacement. So 2,491 is really close to 2.5 liters. Each individual cylinder is 415 cc's. So think about a 400 ml beaker. That's how big the piston is, and there's 6 of them in this engine. So there's 6 little 400 mil beakers with those pistons pushing around, and that's enough to drive that 1,000-pound vehicle at 70 miles an hour. It's pretty crazy to think about. And you're just squirting, you know, 1/10 of a mole or less of gasoline in there and burning it. And of course, you change any one of these things, you can change a little bit about the cylinder displacement, and so on, change the volumes. So now if we have the compression ratio and displacement, we know these volumes here, so that's why they're checked off. We might have to make some assumptions in terms of cold and hot. You can look at your engine temperature and find that the cold temperature would be the radiator temperature. So like 210 Fahrenheit. If you're looking at your temperature of your engine, you're measuring the temperature from the water that's coming out of the engine, the coolant that's coming out of the engine. So that's going to be the lowest temperature that your cylinders are at once your engine is warm. And then the hot temperature would be the combustion temperature. And so that's a question mark. I don't know that. It's hard to find that number because it fluctuates a lot. When you hit the gas, what happens? Well, that temperature goes up and you generate more work, more torque, and you push harder and you accelerate. If you let off the gas, it cools down a little bit, so you slow down a little bit. So you're really pushing that hot temperature up and down with the accelerator. But if you were to assume a temperature here, then with that T hot, T cold, you could find VB. Now this is the real trick. What curve do I use to find VB? Don't cheat and look. Look at the diagram. Okay. So I know a T hot, I know a T cold, I know either VC or VA, right? Which do I use to get VB? So here, this is the one I want to find, right? I want to find this volume right there. And so I want to find where this adiabat hits this hot temperature. So I know I'm using the T hot because VB is on the T hot line, but I've got to use the adiabatic relationship with VC. So it's connected to VC with an adiabat. Okay. It's connected to A with the hot temperature. So T hot, and this is T cold. So I know T hot, I know T cold, and I know VC. So I've got 3 of my 4 variables. So up here I've got, the temperature at C and the temperature at B to the 1 over gamma minus 1 times VC. It's connected to C, point C with an adiabat. If you're going to mess this up on the test, you're probably going to use the wrong volume. So I see people use VA all the time, and they mess that up. Yeah. And so this is the key right here, is to use VC. The other place I see people screw up is they will put this at T cold. So this one is not T cold. And this one down here, let's see, this one is not T hot. You've really got to compare it to the diagram. Notice these are isotherms. So A and B are on an isotherm. They have to be the same temperature. So this is A, right? This is B. They're the same number. They're on an isotherm. And then this is C and D. They're on an isotherm. So there's a big break right here between the T hot and T cold. A and B are at the same temperature. C and D are at the same temperature. Make sense? Look at the diagram. Always, always, always check your work by the diagram. You go fill out your table, the units are all going to work out. Even if you use VA incorrectly, the units are going to work out. You've got a temperature column. You've got 4 temperatures, really 2 temperatures in pairs. But you could get those pairs wrong and not know it. And so I really try to like put on an alarm bell and red lights when I come across a calculation where units won't help you. Because most of the time I tell you, follow the units. They'll fix everything. But in this case, if you get the wrong rows and the wrong numbers, then the units aren't going to help you. But the chart will. And it won't make any sense if you get these numbers wrong in the chart and you compare them over there, because then you'll have like the temperature of B be a lower temperature than the temperature at C, and that won't make sense, right? So we could use these adiabatic relationships to calculate the volume of B by connecting it to C, and then we calculate the volume at D by connecting it to A. See over here, this volume of D is connected to A with an adiabatic relationship. And then we also have T hot on top and T cold on bottom. 1 over gamma minus 1, etc. And so, and for 1 over gamma minus 1, so let's say, what was water's gamma? Just look that up. It was weird, like, but do the fractions. What was it? 4/3. Okay, so 1 over gamma minus 1 is equal to 1 over 4/3 minus 1. Well, what is 4/3 minus 1? That's going to be 3/3, right? So 4/3 minus 3/3 is 1/3, and then 1 over that is going to be 3. So this would equal 3. And so then you can just put that as 3 for water. Now, if you're dealing with a linear molecule like CO2, then you're going to have a different gamma and so on. So that's why we leave it as 1 over gamma minus 1, because it depends on the gas that you're using. But that would be a lot easier. Just go ahead and calculate that as 3 than as some fractional number, I guess. Okay, so that's it. Let's go ahead and calculate some of these just as practice. So let's go back to our numbers here. So let's practice our volume column, our temperature column. So let's say our temperature column was really hot. Let's just make it, 1,000 degrees. Let's see. Let's go with Kelvin. It'll be easier. It's not that hot. Okay, and so this is going to be point B and point C. And so VC is here. And so VC is equal to our cylinder volume, so 415 cc's plus 415 centimeters cubed divided by this 9.03 minus 1. And the compression ratio, since it's a ratio, is unitless. So we have it in terms of volume. Okay. So what is that number? One more time,
466.68.
Okay, we'll say 467. All right, so that's our volume here. And so see, we have our 2 temperatures and our one volume. Okay, so VB is equal to VC. And now which was the temperature on top and which was on bottom? So look at the relationships on the previous page. Pardon? Hot over cold, okay. And it was to the 1 over gamma minus 1, right? So that's our relationship. So we're solving for VB. So that's equal to 467 centimeters cubed times 1,000. This was, so boiling water was 373 Kelvin. And I was looking at the temperature of 210 versus 212. Like 212 was, so I just picked a number slightly less than 373. And so 360 Kelvin is what we'll go with, just for grams. And this was 1 over gamma minus 1. So what you want to do water? We just determined that for water it was 3. So water. So what is this 1,000 over 360? 2 point something. 2.8 cubed.
I think it's cool.
Yeah, do we have our temperatures upside down?
Yeah.
Because what we're doing is we're getting, and this is, so let's go ahead and calculate it. Let's go punch that number in, and let's think about what our chart. So we're going to catch an error. We've made an error, so let's punch our numbers in. Okay. So I already know right now this is going to be larger than 4.67 because it's greater than 1 and it's cubed. So so what did we end up with? Yeah, 10,000. I said greater than 10,000 centimeters cubed. So if we look at our Carnot cycle here, this is VC. It's the largest one. VB should be smaller. Right? And we're coming out way out here somewhere. And so what we need to do is we need to switch that T hot over T cold.
And that gives a little bit too.
So what does it do?
The end number volume is a little bit under 21.8.
21.8 cubic centimeters?
Yeah.
Wow, that's really small. And so then that would be way, way up here. But it is smaller than VC. What we would check to make sure we didn't go too small is just compare it to VA. If it's less than VA, then I don't know, that's weird. Yeah, I don't know how it would be, but yeah. So always calculate your table variables and check them against the chart to see if they make sense. And this is a perfect example. We got the temperatures upside down. No, again, no fault of our own. We make those mistakes, but we can always check to see if it makes sense. VC should be the largest volume. VA should be the smallest volume. And so VB and VD should be somewhere in between. All right, excellent. So we'll do some more practice on that next time.